Okay, so this lecture is on measurements and units, just that first part. This lecture will be broken up into different parts. Let's see, share screen. Come on. There we go. So measurements are critical in data collection. And that may sound like a simple statement, but it's more complex than that. I like this quote from G.K. Chesterton, because he talks about you can construct science with very few instruments or very plain instruments. It's true, science doesn't have to have fancy instruments, but you cannot construct science with unreliable instruments. A man might work out the whole of mathematics with a handful of pebbles, but not with a handful of clay, which was always falling apart into new fragments and falling together into new combinations. A man might measure heaven and earth with a reed, but not with a growing reed, which means you have got to have absolute defined units of measurement when you're working out a problem, taking data collection, working out mathematics. Different aspects of measurements we're going to cover. Making the measurement, including units. Significant figures, that'll be a separate lecture. Accuracy and precision, what's the difference? Scientific notation, and why do we care? That's actually very important, using scientific notation, which you'll see. The measurement unit system we use is the metric system in the lab. And at the end, again, a separate lecture will be unit conversions. Very, very important in chemistry. You'll get really good at those. Whoops. Okay, that last slide just was again on the scientific method. Measurements are part of your data collection step of scientific method. So making measurements, what does that mean? What is a measurement? Why is this, sorry, I have a bar here that's, won't go away. We talk about measurements all the time. What is it? Well, you can have a qualitative observation, which we consider not really a measurement, but that can be the color of something, the texture, the smell, is it heavy or light? You know, what can you observe? What can you feel? The tactile. And they can be very important when you're talking about organic chemistry. Perhaps you've made something and you're going to describe it as powdery or crystal. Is it white? Is it off-white? But quantitative measurements, quantitative observations are measurements. So you have both qualitative and quantitative in chemistry, in any science really. A measurement must have a number and a unit. A number by itself is useless. They change Zoom on me and I hate it. Okay. So this is really critical. A measurement is a number and a unit. Without, if you give me just a number, it's useless. If I give you 25, hi, there's 25. Are you excited? No. Because 25 what? Am I giving you 25 free points on your test? You'll be excited. Am I giving you 25 cents? Yawn. Am I giving you $25? Okay, that sounds better. But if I just tell you I'm giving you 25, that's useless. You're like, yeah, and so what? You must have a unit. Every number must have a unit or it's useless. So remember that. And so we talk about a unit. Now we use the metric system, but initially when you practice conversions, you will be using standard as well. So if I say, okay, sorry, I'm trying to open my pen here. Let's say I'm going to say 1 foot. What's a foot? Well, it's 12 inches. What's an inch? What defines that unit? Units are established and stored with the International System of Units, the SI. The SI contains definitions of 7 base units that originally were determined on defining constants. So I won't go into how they measure these, but it's actually quite interesting. But they are measured absolutely. SI was originally formed in 1875 by 17 countries so that each country would agree on what this measurement was. So you could crosstalk. So if one country says, I've measured something in 13 grams, another country says, okay, yes, I know what a gram is. Now, not quite 2 years ago, in 2018, it was revised, which was interesting. So now the measurement system is based entirely on physical constants of nature. That's just a little side note. So measurements are defined, units are defined, and that's important. So a measurement is a number with a unit that has been defined as part of data analysis. Now there are 2 types of numbers. An exact number is going to be the same no matter who takes the measurement. So if you count pennies as the example, if I count pennies, I'm going to count 7 pennies. If someone else counts pennies, they're going to count 7 pennies. But if I'm looking at a volume of liquid in a graduated cylinder, I'm eyeballing that. I might have a slightly different measurement down to the very last number than the person next to me. So an exact number is something that's not going to change no matter who is counting or measuring it. 7 pennies is 7 pennies is 7 pennies. It's never going to be anything else. The other example, and the one we are going to use most, is by definition. So when you are using a unit in your conversions, 12 inches for 1 foot, that is an exact number. And this will come into play when we talk about significant figures. So keep in mind, an exact number is literally a number, 1, 2, 3, 4, 5, 6, 7, that you count, or a unit definition. Those do not count towards sig figs, significant figures, which we'll get to later. But know that these are called exact numbers. Anything else that's measured on, see, this scale is not an electronic scale, so you have to read in between these lines. 2 different people might read that slightly different. That difference is called uncertainty. And we use a specific way of deciding uncertainty. So I'm going to go back to my whiteboard, which again, they've made hard to get to, and I hate it. Sorry. All right. So, and there we have some examples. I have some examples coming up of what I mean by uncertainty, but I want you to just follow these rules. Unfortunately, I can't show this board and the slide at the same time, but the steps for determining uncertainty are this. What is the largest, or the major? The major increment. Because when you look at a ruler, when we go to the centimeter side, you have your larger lines, right? That's your major. And then you have your smaller lines. That's your minor. So maybe that's 1 centimeter and that's 1/10 of a centimeter. So your major, what's your major? That just warms up your brain. What's your minor increment? What is the smallest increment that is shown on your measuring device? In this case, it would be these guys, okay? What is the unit for that? So I'm going to use my ruler here as an example and say my major is 1 centimeter. It's 0, 1, 2, like that. My minor is these little lines. So here I would say 1, 2, 3, 4, 5, 20, 40, 60, 80, and 1. So 0.2 centimeter, right? That's the unit of my minor. It just is in this example. My uncertainty is if I have something that I'm measuring, let's say it goes to right here. Okay, ignore the back part here. And so it's in between my minor lines. Well, what's that number? Because that's part of your measurement. That in between is part, and that is your uncertainty. So in this example, I know it's less than 1. It's 2, 4, 6. It's at least 0.6 and not 0.8, because that's what these increments are. I'm going to guess maybe 0.2, 0.4, 0.6, 0.8, 0.7, but you can't just call it 0.7. And here's the thing. Your uncertainty is this decimal place. Here's how you get it. Divide the minor increment by 10. Okay. That gives you the definition of your uncertainty. So here, my uncertainty, and we'd call that plus or minus, is going to be 0.02 centimeters. What does that mean? It means that my reading and somebody else's reading is within this of being the real number. That's the uncertainty. We can't be absolutely positive. So your measurement must be to that decimal place. This is one of the biggest mistakes I see. Your measurement and your uncertainty must agree by decimal places. So, and zeros count. Zeros are numbers. So if I say this is 2, 4, 6, I want to call it 0.7 something centimeters. I have to have something here because my uncertainty is at the second decimal place. So 0 counts. That's acceptable. Plus or minus 0.02 centimeters. So you actually would only write the unit once. You would write it at the end. I always run out of room. So I'm going to rewrite this. Nice thing about recording, you can back it up. So I would give my answer as 0. I would say 0.70 plus or minus 0.02 centimeters. That's my measurement. But someone else might say, oh, it looks like 0.69 plus or minus 0.02 centimeters. Right? What this means is plus or minus means the actual measurement is somewhere in between 0.68 to 0.72 centimeters. The actual number is somewhere in there. We don't know where exactly. That's why we call it uncertainty. You can call it estimate. That's fine. You can call it eyeballing. The term you're going to see, though, on exams and on the final is uncertainty. So there's your steps. Find your major increment. That just helps you warm up your brain. What is your minor increment? Divide your minor increment by 10. That is your uncertainty. It is. And then make sure you include it in your answer and your measurement is at the same number of decimal places as your uncertainty. So do this step and then go back and give your measurement. And before you finish, double check that this is at the second decimal place, so that's at the second decimal place. Okay, going back to the slides. All right. So that final digit, and how do you know where it is? First figure out your uncertainty and then say, okay, it's at the third place in this case. So my measurement has to be there. 0 is fine, but make sure you put it. Unit goes on the end. Because different people are going to have a different number for that as estimated. So that's your estimate. It's your eyeball. We call it uncertainty. Next, please. All right. So here's an example. Here's a step-by-step of what I just did. So go ahead and just follow through this on your own. Pause, work through it, use it as a reference. Once again, step by step. So here's what it looks like. Here's one of the reasons it makes a difference. This is the same piece of wood, piece of blue stuff, right? Against 4 different measuring devices. We're going to skip this one. How precise you are depends on the precision of your measuring instrument. Here I have a ruler and it only has markers for major. So what's my major? 1 centimeter. What's my minor? It's 1 centimeter. And so it just is. So divide that by 10. What's my uncertainty? Plus or minus 0.1. I'm telling you, I hate the changes they made on this. Zoom's update was a down date. The major unit increment is 1 centimeter. The minor is also 1 centimeter. It's the same, major and minor. There's no little lines. So uncertainty is 1/10 of the minor. So it's 0.1 centimeters, right? 0.1 centimeters. So my measurement, so let me go back to my whiteboard. So erasing this. And I wish I could have both up, but I'm afraid I can't. So the example, the major was 1. But the minor was also 1. It's okay. There was nothing else. Uncertainty is this divided by 10. I'll put it in parentheses. Okay. So that's my uncertainty. Now that It was between 3 and 4. I'm going by memory here. And I think it lined up something like that. So my measurement is going to be at least 3, but not 4. My uncertainty is at that decimal place, so my measurement has to be at that decimal place. So it's going to be I'll say 3.7. Now, you might say 3.6 or 3.8, and that's the point of this. So I'm going to write it as 3.7 with that. Unit comes at the end. So my number, my uncertainty, my unit. Check, make sure, yes, my uncertainty and my measurement have the same number of decimal places. It's the same decimal place, rather, not the same number. So that's my measurement. You might look at it and go, well, that looks more like 3.6. So you would write 3.6. That's fine, because what this means when I wrote it, it means my measurement is anywhere between 3.6 to 3.8 centimeters. Anywhere in there is the correct measurement because of uncertainty, because it's an estimate. This is an estimate, that digit. It's the wiggle room. It's the guess, you know, the estimate, the eyeball. So if we go by the steps, the first measurement is going to be 3.6 or 3.7. So let's go back to the slide. They broke it. All right. So the first one would be, we'll call it 3.6 or 3.7. So I'm going to say 3.7 plus or minus 0.1 centimeters. Now, I'm just going to jump down to here. This would be, we'll look at it. Major is 1 centimeter minus a 0.5. So your uncertainty would be 0.05 centimeters, and your reading has to be with 2 decimal places, so 3.85 centimeters. That's what I'm going to say. I'll say 3.85 plus or minus 0.05 centimeters. This 0.5 divided by 10 is 0.05, and that goes over here. And then we're backwards. This one has 10. So my precision just increased because of the precision of my measuring device. Now, my major is still 1 centimeter. My minor is 0.1 centimeter. So now my uncertainty is 0.01. You notice the uncertainty is getting smaller and smaller and smaller, which means that that narrow window of what the measurement is getting tinier and tinier. You're getting more precise. So I'm going to say 3.9. But remember, my minor is 0.1, so my uncertainty is 0.01 centimeters, right? 2 decimal places. If I say 3.9, that's not correct. Because 3.9 does not have the same number of decimal places as my uncertainty. So let's go back to the whiteboard again. Keep that picture in mind where that line is. Okay, so this was without any little lines. And remember, that was off memory. But this time we have all these increments. I don't want to draw 10, just 2, 3, 4. All right, fine, I will. 1, 2, 3, 4. And it was kind of right here. So my major is still 1 centimeter. My minor, however, is now 0.1 centimeters. That's the little line. That's in that ruler. So my uncertainty is 1/10 of this. Just do that first. Okay, always do these 3 steps first. Very first, now go back and do your measurement. So I looked at it and I said, oh, that looks like 3.9 centimeters. That cannot be my measurement, right? Do you see? Because once I put my uncertainty in here, I'm just going to drag this down here. Whoops. What do you see? You see that this one is at the second decimal place, but I don't have a number here. So what do? I put a 0. Because 0 is a number that matters on the right-hand side of the decimal place. Now my number is correct. That is an accurate measurement. And what that is saying is that, okay, it's between 3.89 centimeters and 3.91 centimeters. Look at how much more precise my number got. Before it was between 3.6 and 3.8, or it could have been 3.8 to 3.9. We just got a lot more precise within 0.100th of a centimeter. So that's just some examples. So when you do uncertainty, first 3 steps, don't even think about it too much. Go through them. 1, 2, 3. Write down your major, or in your head, write down your minor, take 1/10 of your minor, that's your uncertainty. Now go back to your measurement and make sure your measurement has the same number of decimal places as your uncertainty. You're good to go. You don't really need to overthink it as long as you follow the steps. You will find I'm a big fan of algorithms. There's plenty, I get confused easily. There's plenty to get confused at, so don't add to the pot. All right, go through those steps and you'll be fine. Okay, back to the slides. So here are some examples of different types of measurements, different types of scales, we'll call them. You have a speed dial. All right, what's your major? It's 5 miles per hour. Remember, don't forget your unit. So what's your minor? It's the same. It's 5 miles per hour. So sorry, went off in thought. So my uncertainty is 10% of the minor, which in this case is the same as the major, so it's 0.5 miles per hour. So my measurement has got to be 1 decimal place. So I would call that 11.8 plus or minus 0.5 miles per hour. Now a graduated cylinder is built to contain. That's what we pour liquids into to measure. So it counts up because it's holding a volume, and you have to figure out what the volume is, 3.54. A burette is to dispense. We use it in titration, we dispense, and so we're actually measuring how much volume we've gotten rid of. And so notice that it reads backwards. So when you read a burette, make sure you read it in the correct direction. Start at the 3 and go towards the 4. I know that sounds oversimplified, but it's really easy to get that one mixed up, believe it or not. So 2, 4, 6, 8, 10. So that's 0.2, 0.4, 0.6, 0.8. So my minor is 0.2. My uncertainty is 0.02 milliliters. So my measurement is going to be 3.2 something, second decimal place, plus or minus 0.02 milliliters. Thermometer, you read up, and there's our ruler again. There's the little quiz on the other end, see if you can find the right answer. And I can go through this in the live lecture. All right. Repetition, as I said, is critical in experiments. In carpentry, you've heard measure twice, cut once. When we're doing experiments, you do at least 3 reps, preferably 5, to feel confident in your number, in your data, because there can be reasons that the numbers are wrong. And that's when we talk about how good the measurement process is. go over these in class, but look over these, the definitions of precision and accuracy. Precision is reproducibility. You have a series of numbers, how close are they to each other? So this is a good grouping. This is very precise. But accuracy is how close is it to the actual number? This is very precise, but not accurate because the accuracy is over here. So just review these slides and the difference between them and why they matter. Okay. And the other thing is the different kinds of error. Systematic error is often because of an instrumental issue. If you do spectroscopy, you might have a reading due to the liquid that your substance is in that you're measuring. It's giving it a false high. A systematic error, you can usually determine what it is and you can correct for it amongst all your data. So systematic error, once you have, it's going to either increase or decrease your data by the same amount or the same percentage all the way across. So once you find what that is, you can correct for it. Random error, on the other hand, is what we call human error, and that is, or operator error, you cannot correct for, which is another reason for taking multiple reps of something. The more data points you have, the easier it is to see which are the outliers, which are the really wrong numbers. Because of human error, we just throw them out based on statistical manipulations. We don't randomly throw them out. You have to do some statistical manipulations to determine, yeah, this really is an outlier. So systematic error is generally instrument error. Random error is generally human error. Sometimes it can be depending on what you're working on. I'm sitting in a room that's quite warm. Humidity can play an effect, you know, atmospheric conditions, especially in Florida. So there are all different kinds of error, random error. The point is you cannot correct for them because it's not any specific increase or decrease. That's the end of this one. Sig figs will be the next lecture, so we can break this up in bits. Again, I'm going to go over this in lecture and email me with questions.